Good morning all. We will see the continuation second unit part of the transmission lines, wherein we have different topics. We will start with the analysis of what is reflection coefficient exactly speaking about. In this slide, the diagram is very clear. The word very clearly depicts reflection coefficient. The plane waves reflecting off water are described with the reflection coefficient. In the diagram, how the waves are seen on the surface, how it is incident on the surface. So incident wave and the reflected wave, how it is seen under the analysis of the surface. So that is reflection condition. So by definition, the analysis of reflection coefficient is very clearly viewed in this diagrammatic analysis. Now we will go into the mathematical definition. As we have seen that a transmission line can be connected between the source and the load, I have two definitions of impedances. The input impedance seen through the transmission line defined in terms of the characteristic impedance Z0 and the load impedance ZL. So how to define Z0 first? Z0 is a characteristic impedance which is mathematically defined as the ratio of incident voltage to incident current or reflected voltage to the reflected current. Either take the incident analysis or the reflected analysis. So it is incident voltage to the current analysis, same as that of the Ohm's law, V by I equal to R, but it is spoken in terms of the characteristic impedance. Now, what is total voltage? Total voltage can be the sum of incident voltage and reflected voltage for the difference of incident current and the reflected current. Now, how to define the load impedance from the definition of total voltage and current? It is the ratio of total voltage to the total current. So, it is defined by Vi plus Vr divided by Ia minus Ir. So, reflection coefficient is generally denoted by rho. Tau, sum of the analysis, small rho, capital rho, whatever they choose that to be. Some books define K, which is ZL minus Z0 divided by ZL plus Z0. Or it is the ratio of VR by Vi or IR by II. That is reflected voltage to the incident voltage or reflected current to the incident current. Again, for a lossless condition, the same definition is held in terms of general definition. If rho is equal to ZL minus Z0 divided by ZL plus Z0, then minus rho is the reverse condition. In the mathematical equation, we can also include V0 minus and V0 plus, one more term with regard to RF. So it is reflected wave is always denoted by V0 minus and incident wave is V0 plus. So it is the ratio of reflection to incidence. So minus rho is also possible. So generalizing the equation mathematically, reflection coefficient is defined by magnitude of reflection coefficient and the phase of e power j theta. So rho is equal to rho e power j theta, and the load is matched to the line when ZL is equal to Z0. We say that the line is exactly matched whenever the load impedance is equal to the characteristic impedance and such that V0 minus is equal to 0, and also your analysis of reflection is made equal to 0. And finally, the reflection coefficient can be defined in terms of three set of conditions: when it is terminated in Z0, when the transmission line is short circuited, when the transmission line is open circuited. When it is terminated in Z0, the reflection coefficient is 0. When it is short circuited, we are making ZL to be equal to 0. So it is minus 1. When ZL tends to infinity, rho becomes equal to 1. This very clearly depicts us the analysis of reflection coefficient in general. Thank you. So we'll go to the analysis. In the next analysis session, we will study about the relationship between the reflection coefficient and the SWR analysis.